All right. All right, let's go then. Sorry for the delay.
You're fine. Dane
My name.
Courville, everyone. Dane Courville. Vertical curves tonight.
Okay.
All right.
So let me make this slideshow or view.
You had it under slideshow and then presentation mode. Yeah, there and from from the beginning, I think it's fine.
Oh, okay. There we go.
Go.
Can y'all see it now or no? Oh no.
Still just on that thing.
Yeah, it moved at different screens. Oh well, I'll leave it right here. I'm not going to complain.
Got it.
It looks perfect for me.
Yeah,
Okay. All right. So vertical curves. The way I explain vertical curves is I go through all of these 6 elements, or actually 5 elements. The last one's example. So on the exam, you will be provided a equations or formula sheet. I highly recommend that y'all all go download it. I think I mentioned this with horizontal curves. It's called NCEES handbook, reference handbook, and it's a free download from the NCEES website. Trent, maybe we can make that available for everyone too. I have copies of it. Let me see if I can find it really quick just to show y'all what it looks like. This should be your go by while studying. You should have this downloaded and constantly looking at it. That's what I would recommend. Let me see, where is it? Equations. I have 2 of them. One I did, I have a bunch of notes on it. It's probably this one. Okay. No, yeah, this is the good one. Okay, it could have been updated too since I last downloaded this, but here it is. FS Reference Handbook. It's by NCEES. And all it is just all your equations, and you're going to be given this on the exam as a go by. Okay. So here's horizontal curves. When you go down to vertical curves, here you go right here. It's going to give you a diagram. It's going to label all the parts for you of the vertical curve. And then it's going to give you the relevant equations that you need to utilize to solve their problems. Now, when I wrote my manual, I use this equation sheet as my go by. So in my manual, I cover in my topics every single aspects of this equation sheet, and I explain these and how to solve them. Okay. So back up to vertical curves. So on the test, you'll be given that diagram. So the elements and terms are going to be provided to you. And that's not to say that you shouldn't be very familiar with them. You should, but you don't have to memorize them. Okay. If you do enough problems, you're going to have them memorized. Number 2 are the 4 components that they call for of horizontal curves. And we're going to get to all this. And then 3rd is the knowledge of the distances associated with vertical curves are purely a change in X value. They're all flat. And I was at the WFPS conference teaching this, and someone came up to me after, and they said something that made total sense. And I can't wait to say it when I get to this part right here. And then we have the equations, which again are provided, but we need to know how to utilize them. Okay. And then finally, what are the characteristics of a vertical curve? So we're going to go through these 5 elements. If we have time, we'll go through an example. The best way to learn this stuff is going through, having an example, like a real life example. Okay. All right. So terms and elements. This is my depiction. It's a lot like the one provided on the exam, but I go through and I label all the aspects of a vertical curve, and I tell you what they are right here. Okay. I can provide this PowerPoint to Trent if anyone needs it after as well. So just understanding how the vertical curve works is what I'm trying to get at here. So if you look at my paper where I'm going to be drawing, we have a straight line coming in. Okay, let's say it's a road. Okay, I know it's a pretty damn steep road, but we got a road coming in. We're going to hit a point of curvature, vertical curvature. Okay, and then we're going to get to another point where the road becomes straight again. Now, keep in mind, this is a hill. All right, we're going up a road. The car is struggling to go up. It's going over the curve, and then the car can start to finally come down the hill. Okay. We have this straight coming in is called G1, grade 1. It's also called the back tangent, because if you extend this out, an extension of that grade, this is called the back tangent line. And then you're going to have your curve, and then you're going to come to your G2, which is your straight line exiting the vertical curve. And if you extend that, you're going to get your forward tangent. So here's your forward tangent, and here's your back tangent. Now, for me, this is counterintuitive. And that's how I memorize this. My back tangent is the curve coming in. Okay, it's on the back side, but it's how you come into the curve, which doesn't make sense to me. If anyone can explain that to me, I'm open, I'm all ears. But, and then you have your forward tangent, which is on the exiting side. Okay. So this right here, where the curve starts, is your PVC, point of vertical curvature. This is called the point of vertical tangency, because you're coming back into a tangent line. And where those two tangents intersect, that's your PVI, point of vertical intersection. All right. And just like a horizontal curve, you're going to have your chord, you're going to have your external ordinate, and you're going to have your actual curve. All right. We'll get to how to solve these here in a minute. I just want to go over the idea of a vertical curve. Now, you might have a vertical curve that is a valley, right? You could have a road coming down a hill into the vertical curve, then you coming out the hill, like a ditch or a railroad or something, right? So this type is called a crest, and this is called a sag. And I'm going to show you a mathematical formula how to figure that out based off of these grades. Now, a lot that we deal with vertical curves is going to be associated with these grades, okay? Your grade coming in, your grade coming out, your straight lines coming in, straight line coming out. Now, grade is another word. It should be synonymous with you with the word slope. It's the same thing. Grade and slope are the same thing. And you should know that slope is designated with letter M, but also it's the change in Y over the change in X. I like to look at it like a staircase, okay? You have your stairs. And here's your XY Cartesian graph, okay? You got your Y-axis and your X-axis. Now this staircase is going to be changing along the X-axis, and it also changes along the Y-axis. So for every foot, let's say these stairs are a foot rise and a foot run. A foot rise, it goes up a foot, and a foot run, it goes out a foot. So 1, 1, 1, 1, okay? So I'm going to go up a foot, and I'm going to go over a foot, up a foot, over a foot. So from this point to this point, what would my change in Y be? My change in Y, I just want to know what it is from here to here. That's my change in Y value. And I've changed 1, 2, 3, 4, 5 feet in that span. And my change in X is going to be the distance I travel along my X-axis. So for this, I'm going to travel 1, 2, 3, 4, 5 feet. So in this situation with the 1-to-1 step, I'm going to have my slope change in y, which is 5 feet, divided by change in x, which is 5 feet. I have a slope of 1, positive 1. So this line has a slope of positive 1, or a grade of positive 1, okay? And this can alter. I can have a staircase that goes up half a foot and has a run of 3 feet. And I can figure that out. Up half a foot, 3 feet. However long I go, I know I'm going to know my change in x, my change in y, and I'm going to be able to figure out my grade. So understanding that concept, as simple as it is a major part of vertical curves, okay? Slope is grade, grade is slope, and all grade and slope are simply are change in y over change in x. When you're doing other survey problems, you're going to realize that change in y is your latitude and change in x is your departure. Same concept, okay? So we got slope. Now, also, they're going to give you, all your problems are going to be provided to you in percent grades. It'll say like -2% grade, okay? That value is not usable. You need to convert this to decimal degree for your formulas to work out. So -2% is not okay. But if you convert that percent to a decimal degree, -0.02, that's the number value you're going to have to plug into your equations when you see the letter G or the letter, G1 or G2, okay? This will get you every time. Make sure you make this conversion, okay? Even if they ask for an answer, they're asking for what's the percent of grade leaving the curve. Well, you're going to have to convert this grade, do all your math, get that grade. It's going to be, -0.01. And then you might have to convert that back to percent to give them the right answer, which would be -1. But that has to be done. Your formulas, your equations will not work out if you don't make that conversion. Okay, and I have that right here. It's a simple conversion. Percent divided by 100 gives you decimal percent. Decimal percent times 100 will give you your percent. Okay, if you memorize that, you'll be all set. It's pretty simple, but you will have to do that. Don't start plugging in whole number percents for your values. And I'll show you when we get to those. All right, so we've gone through all the terms and elements. Again, this can be provided to you. I want to point one more thing out on this page, though. And it's one of my focuses here, and that is this number 3. Understand distance and length or simple change in x value. What do I mean by that? This vertical curve, this chord length right here. So I'm back to my drawing. If I have my curve and I have my chord here, point of vertical curvature, point of vertical tangency. All right, and I measure along this chord. In order for me to measure along my chord of a vertical curve, I would have to drill into the ground, okay? And get that physical length from this point to this point along this line. Let's say that is 105 feet, okay? That is not the distance that you need to be concerned with. The distance you need to be concerned with, back to my Cartesian graph, is the distance from here to here on the x-axis. I need to know my horizontal distance, not my slope distance, okay? You will not need to know that actual physical chord length. You just need to know what is the change in x value from this point to that point. All right. So if this point was 0, 0, and this point was 5, 8, my change in X would be 5 feet, right? 0 and 5. I'm going from 0 to 5. So this is 5 feet. I know it's drastic. That line that in this example, it would look something kind of like this. If I'm only going 5 feet with a 105-foot long line, it would be something like that, right? So that's 105 feet. But that 105 feet only carried me 5 foot, horizontally speaking. The gentleman at the conference explained this, how to explain this would be, you got to think of a vertical curve as presented to you on a flat map, right? Like a road alignment. When you see a vertical curve on a flat map, you got your road right here, okay? And there's a vertical curve in this gap, okay? The road's, you don't see it, but the road's coming up and the road's curving and it's coming back down, okay? So how would I draw a vertical curve for this road right here? It would look like a straight line, okay? The road elevation at this point could be 1,000 feet. The road elevation at this point could be 0 feet. I'm traveling vertically 1,000 feet as I drive this. But if you're looking at it on the plan, it's flat, right? Well, that's why these values are going to be at change in X values. I don't care how much the slope distance is. All I care about is how far I traveled along my X axis. So lengths and distances are always interpreted or obtained through change in X value without the consideration of elevations or change in Y value, okay? And in my diagram, you'll see that I'm trying to show that. So I have back to my PowerPoint, I have my vertical line here, but my distance that I'm concerned with is a flat distance along my X-axis, okay? So think of something drastic like this diagram right here. I'm only traveling 5 feet horizontally, but along elevation, I'm traveling 105 feet. I don't care about that. I just care about that, okay? And these are the values that you'll be plugging in to the equations, not the long slope distances, all right? Okay, so those are the components. These are the parts. We understood slope and grade, and the counterintuitiveness of back tangent being on G1 and forward tangent being on G2. The way I memorize it is I think, oh, that doesn't make sense, okay? All right, next part of the 4 components of a vertical curve. I'm back to my drawing. The 4 components of a vertical curve are slope, AKA grade. We got change of grade, which is designated with A. We're going to have rate of change of grade, which is little r, not to be confused with radius. And number 4 is the parabolic constant. All right. And when we go through these, I'm going to go through them in this order. And you'll see why, because they all build on each other. This one down here has all the concepts built into it. Okay. All right. So we'll do slope first, which we already did. Slope is very simply known as grade. Grade is known as slope. And all they are is simply the change in Y over change in X. Just think about the staircase situation. Okay. I'm just talking. Does anyone have any questions so far about terms and elements and all that? Okay.
Nobody yet.
All right. Number 2 is change of grade. Now, the difference in grade between, all right, what is change of grade? Change of grade is A, and it's defined as, what's the difference between my 2 grades? Remember, I had G1 coming into the curve, and I had G2 coming out of the curve. I have a grade coming in and a grade coming out. All I want to know with A, change of grade, is what is the difference between the two? Essentially, I'm asking for the angle. Think about it as the angle between those two grades. We're not even talking about the vertical curve yet. We're just talking about these two grades. And how does one differ from the other? And it's simple. It's the G2 minus G1. That's it. G2 minus G1. So the grade of G2, line G2, minus the grade of line 1. In other words, the grade of the line going out of the curve minus the grade of the line coming into the curve. That's all you got to do to figure out A, change of grade, and think of it as an angle, the difference between those two grades. This value is going to tell you a lot about the curve that you're dealing with, okay? Let's see. I do it here, but if the value of A is positive, you're going to have a sag. Your vertical curve is going to look like this. If you have an A of negative, your curve is going to be a crest, a hump. Okay, and let's figure that out. Well, first off, we got to figure out slope. So negative slope, your line is going to travel from left to right. It's going to travel downward. That'll be negative slope. So if you're reading, the direction you read, if you're going down, it's going to be negative. In the direction you read, if you're gaining elevation, your slope will be positive. So negative slope, positive slope in the direction you read. Okay. So my staircase example, I'm going to have positive slope. I'm gaining elevation. I'm increasing Y value as I move from left to right. All right. So let's do this. I have a curve and I have that and that. And here's my curve. Let's prove, just by looking at this, I know my A value is going to be positive. Okay. So my grade coming into this vertical curve, grade is slope, and my slope is going to be negative in this situation because I'm moving down in elevation, down in Y value from left to right. So I have negative, and coming out of the curve, I'm going to be gaining elevation as I move left to right. So I know that's a positive grade or positive slope. Let's just assign a number value. They're about the same in severity. Let's say this is 2% and this is 2%. So the formula for A is, this is G2 and this is G1. A equals G2 minus G1. I'm going to change this. I'm going to make this 3. It'll have a 0, and that'll be, that's another topic. All right, so A is G2, which is positive 3%, minus negative 2%. Notice I put my parentheses here. My slope for G1 is -2, and I'm subtracting. That's the formula, G2 minus G1. So minus the minus is positive. So this could really be written as 3 plus 2, which equals 5. Positive 5, just like we assumed. So again, a sag is going to have positive A, positive change in grade, and a crest will have negative change in grade. Same thing. If I have positive 2 here and negative 3 here, it would be -3 minus 2, positive 2, AKA -3 minus 2. In this situation, I'd have -5. So again, my A for this is negative, just like we assumed. So sags are positive, crests are negative. Down left to right is negative with slope. Up left to right is positive with slope. Okay. So A is pretty easy. That value minus that value. Now notice I did not convert my percents. Like I said, we always have to. The only reason I didn't have to in this situation is that's all I'm looking for is a grade. So for me to convert to decimal degree and then have to convert back to percent didn't make sense. But I could have if I would have wanted, and it still works out. Let's do this one. -2%, that equals -0.02% minus positive 0.03%. I'm going to get, oh, wait a minute. -2. I flipped them. This will be -2. This is G1. And then +3. So in this situation, it'll be 0.03 plus 0.02. I'm going to get 0.05, which is the same as this. If I convert back to decimal degree, that divided by 100 equals 5. I'm sorry, times 100 equals 5%. Okay. All right. So that's A and that's M. Those are 2 of the 4 components. The other component is rate of change of grade. So keep in mind your A concept. A was just what is the difference or what is the angle change from G1 to G2. Now, rate of change of grade, it throws in one more element, which is distance. Okay. So not only am I saying, so now we're on rate of change of grade, little r. Not only am I concerned with how these 2 grades differ from one another or what the difference between them is, I want to know what the difference between them is over a certain amount of length. So I'm going to add in length to this formula. This formula is the change of grade formula divided by L. So again, I care about how the difference between my 2 grades over a certain distance. What this is going to do is it's going to tell you the severity of your vertical curve. Think about it. I want to go from this grade to this grade over this distance. Okay. I want to go from here to here over that distance. Well, my curve would look something kind of like this. Pretty mellow and pretty flat, right? But what if I have the same grade coming in and the same grade coming out, and I'm only going this distance right here? So now I got this sharp little tiny hump. Okay. So the difference between this and this is only related to how far apart these grades are. How far apart means distance between them. Okay. So that's all rate of change is doing. It's taking that change of grade and it's adding in the distance between them to figure out what the severity of your curve is. So this one's a pretty mellow, smooth curve. This is a pretty sharp, intense curve, right? That's what rate of change of grade is going to tell you. So we've gone through M, we've gone through A, now we're done with R. The final one is the parabolic constant. And this one's pretty easy. It's the exact, that's going to be designated with a little lowercase a. The formula for it is the change of grade again, and the rate of change of grade. So it's exactly the same, except I just multiply my distance times 2. It's the only difference. Only difference between parabolic constant and rate of change of grade is I'm multiplying my distance times 2. What this is going to do is, this is a constant and is a characteristic of a smooth parabolic curve having a constant rate of change of grade and equidistant tangents. So this parabolic constant can only be applied to symmetrical vertical curves, okay? Which, good luck for all of us, we're only going to be dealing with symmetrical vertical curves on the exam, okay? Just like on the exam, you do not have to worry about spirals. That's an odd horizontal curve because the radius is constantly changing, okay? Well, same thing happens with vertical curves. We don't have to worry about these complex vertical curves. All we have to worry about are vertical curves that have a constant rate of change of grade. So we're not going to have to worry about a vertical curve that looks something like that. Wait up. It's hard. They're hard to draw. Hold on. Something like that. It'd be like that. Okay, like a fish hook, kind of. So in this situation, my vertical curve, it does not have a constant rate of change of grade, okay? Nor are the tangents equidistant, okay? They don't even intersect in this situation, okay? So we will not have to fret and worry about those, okay? And when you don't worry about those, now you can start to apply the parabolic constant, G2 minus G1 divided by 2L as opposed to L, okay? So those are the 4 simple components of a vertical curve: slope, change of grade, rate of change of grade, and the parabolic constant. Now notice I have my formulas here. I have other formulas associated. Well, all I'm trying to explain here is this G2 minus G1, that is A. That is my change of grade. So I can replace all of this with A. So rate of change of grade really could be written as A divided by L, as opposed to G2 minus G1 divided by L. The same thing applies to the parabolic constant. I have A divided by 2L. Well, A divided by L is essentially rate of change of grade. So I can replace that with an R. So really, parabolic constant is R divided by 2. I'm just simplifying them is all I was doing, okay? If you don't want to go down that path, just stick with the longer version, you'll be fine, okay? All right, so those are the 4 components of a vertical curve. And you'll need these for the equations coming up, all right? Does anyone have any questions? All right.
Dane, I have a question.
Yeah. Okay.
The distance L that spans across the horizontal axis, would that distance be the same along, let's say, a horizontal alignment that's flat on a surface?
Yes.
Okay.
Yes. Yeah. That's what I tried to mean. That's what I was trying to explain. So you have a road, you have a map for a road, and you have your alignment with stationing, right? So 0 plus 0, 0. And 1 plus 0, 0. 2 plus 0, 0. 3 plus 0, 0. Okay. Now, when you're looking at this, if you don't look at anything else, you just see a flat road going across the field, right? Well, what if this is on a mountain pass? Okay. And from here, from station 1 plus 0, 0 to 3 plus 0, 0, you change your elevation by 300 feet. So when your car is at this station, 1 + 0, 0, you're going to be at 5,000 feet. When you get to here, if you change 300 feet, you would be at 5,300 feet by the time you reach this point, right? But looking at this on the plan, it looks nice and flat and straight. So your distances you're dealing with vertical curves are along this alignment. They're flat. Okay, it does not take into account the change in y. So if I were to take this and do a profile of it, it would look something like kind of like that, right? So from this point to this point, I'm changing 300 feet in elevation, but I don't care about that. All I care about is the distance from here to here, which is only 200 feet. Okay. So my car may have traveled 206 feet, but I don't care about that. All I care about is my car traveling flat 200 feet. Okay.
Thank you.
Yeah, this is a big concept to try to understand. The math will not make sense and will not work out if you don't use this simplistic flat change in X value of distance, okay? And this diagram that I have drawn up right here, this explains it all right here on my PowerPoint. Okay. Now, also something else I want to point out on this. If I were to draw a perfectly vertical line from my PVI straight down, so perpendicular to the x-axis, a perfectly vertical line. If I draw a line from my PVI straight down, it's going to cut my chord perfectly in half. So it's going to find the midpoint of my chord. Now, if I keep going down, it's also going to cut my distance in half, because so I have a slope line like this, and I'm only changing my x-axis by 100 feet, let's say. Okay. The midpoint here, oh, and this line right here, let's say, is 130 feet along the line. So look at it like a right triangle. That's going to be my hypotenuse. This is one leg of my triangle. This is the other. So again, my car is traveling 130 feet. This is my midpoint. And I only care about this 100-foot change in X value distance. But if I draw a line perfectly vertical down, it's going to intersect this line in the middle as well. And now I'm going to have 50 and 50. Okay. This is all important to know when doing the math for vertical curves. Okay. Does anyone not understand this concept? I don't mind explaining it, because it's the backbone of almost everything we're going to do. Okay, so now let's get into the equations. We've gone through terms and elements. We've gone through the 4 components: slope, change of grade, rate of change of grade, and the parabolic constant. I hope I've drilled into y'all heads. Distance is simply the change in X value. Now let's get into the equations. Yeah, here's another good diagram. Look at the PowerPoint. This is another diagram of the change in X value, okay? Distance. Again, I don't care about the red line. All I care about is this green line here, okay? And what do I mean by change in X? Well, if I start at 0, 0, I end at 13, 8. My change in X is just going to be 13 minus 0, which is 13. So my distance here is only 13. I don't care what the distance is on the road that I'm driving, okay? All right, equations. My paper. We're really going to only have 3 major equations to deal with. We're going to have 2 equations dealing with elevations along tangents. And we're going to have 1 equation dealing with elevations along curves. Okay, so here's my diagram. Got my grade coming in, hit my PVC, got my curve, hit my PVT, come out of the curve on my G2. G2, G1, PVC, PVT. If I extend my grades, these are going to be my tangents, and they're going to intersect at my PVI. Okay. The equations that we have to deal with, there's only 3 of them. Minus, well, there's 3 minus the equations for my 4, or not for the 4 components of a vertical curve, which were the slope, grade, rate of change of grade, and parabolic constant. Those were pretty simple. Then the questions they're going to be asking you are, what are elevations along my curve? And what are elevations along my tangents? Okay. Those are the 2 big questions that they're going to be asking you. If they ask for what are elevations along the curve, there's only 1 equation you got to worry about. If they ask you, what are the elevations along my tangents? There's going to be 2 equations. 1 equation for my forward tangent, back tangent, and 1 equation for my forward tangent. And then there's 1 equation for curve. So these are your 3 equations that you have to focus on. Elevations along here, elevations along here, and elevations along here. Okay. So what are the actual equations? Well, equations for elevations along my back tangent are provided right here. Y PVC plus G1 times X. So what does this mean? Y PVC is a fancy way of just saying, what is my elevation of my PVC? Okay. So Y PVC is what is my Y value, or what is the elevation of my PVC. That's all that means.
Hey, Dane.
Yeah.
I lost your overhead.
Oh, yeah.
There you go.
Okay.
No, perfect. We're back.
Let me plug in.
Oh, phone dying.
Yeah.
Sorry.
All right.
I should have spoke up sooner.
Okay. All right. Can y'all see it again?
Yep, we're back.
Okay. All right. So Y PVC is just a fancy way of saying what is your elevation of your PVC. Okay. Plus G1, which is the grade of my coming in line. This is where you need to convert to decimal degree. You cannot use the 4% value. You have to use the 0.04, okay? Only use decimal degree in all these equations for your grade values. So elevation of your PVC plus the decimal degree value of your grade 1 coming in times X, which is the distance. So to find an elevation along this back tangent here, I need to know the elevation of where I'm starting from. I need to know the slope of that line, And I need to know how far up that line do you want me to go? Okay, which all that, if you think about it, that makes sense. If I'm starting at elevation of 100 and I have a slope of 1, so for every 1 foot of rise, I have 1 foot of run, and I go 30 feet, well, the elevation at that point is going to be 130 feet. Okay, that's all this equation is saying. Now, this x value, how far am I going up this line? Again, let's zoom in. Here's my PVC. And I want to find the elevation of this point right here. X does not mean that distance. X means this distance right here. Again, change in X value. Okay? Please don't forget that. So again, the equation for an elevation along my back tangent is going to simply be my elevation of my PVC plus my slope of this line times the horizontal distance I traveled to get to that point. Okay? That's it. That's equation number 1. Equation number 2 is I want to find out an elevation along this forward tangent here. Okay? Well, what do I need to know to figure that out? That is y of PVI plus my grade of line 2, my back tangent grade, times an x value minus L2, half of L. All right, let's figure out what this means. So y PVI, fancy way of saying my elevation of my PVI. I need to know the grade of my G2, which is, this would be the slope of G2, times a distance I travel from my PVI minus the distance of L. And L is the horizontal distance from PVC to PVT, this distance right here. So if that distance is 300, it would be however far I travel along this line. And remember, not along the line, but the change in X value of how far I go, minus half of my L, which in this case is 300 minus divided by 2, 150. Okay. So, let me see. Yeah. So what you need to focus on for this equation, this one's kind of backwards, because on my back tangent, I just go from my PVC up to my PVI and I'm done. Okay. Well, for my elevations along my forward tangent, it's backwards. I'm not going from PVT to PVI. I'm going from PVI to PVT. So if they tell me the distance from here to here, that's not going to do me any good. I need to know the distance from here to here. So it'd be it would be that distance minus X. And I didn't draw this right. This isn't a perfectly drawn, but let me draw it better. The reason they're saying L divided by 2 was because, remember, I said if you draw a line from your PVI straight down, you're going to cut that vertical curve in half, and you're going to cut your chord in half, and you're going to cut your horizontal distance in half. So really, from this point to this point is, we know the distance from there to there is going to be L, the whole thing, divided by 2. So it'd be half of L, right? L divided by 2. So if L divided by 2 is this half of your vertical curve, which is your forward tangent, and they tell me the distance from here to here is X, well, then this distance right here is going to have to be X minus L divided by 2, which is what they have there. So this is their fancy way of saying you got to move backwards, is all I'm trying to tell you here, okay? So for the elevations along your back tangent, it's simple. Just go your X value and you're done. But to figure out your elevation on your forward tangent, you're actually moving, you're working backwards. You're going from PVI to your PVT, not your PVT to your PVI. And when you do that, you have to add in this little caveat, okay? And again, your G2 value should not be a percent, it should be a decimal degree. So if this is 1%, negative 1%, then it'll be negative 0.01 for that value, okay? Then, so we have the 2 equations for elevations along a tangent. Now we have to do 2 equations, oh, I'm sorry, 1 equation for a point along the curve itself. And the equation for that is y of your PVC plus grade of 1 times x plus your parabolic constant times x squared. Okay, so what does this mean? Well, to get the elevation along your curve, anywhere you want on this curve, you need to know the elevation of your PVC. You need to know the grade that you are coming in at. You need to know how far horizontally you want to go, which would be this value right here, plus that same value squared times your parabolic constant. And your parabolic constant, remember, was G2 minus G1 divided by 2L. All right. This equation right here will give you the elevation of any point you want along the curve. So those are the 3 equations. Elevations along the back tangent, elevations along the forward tangent, and any elevation on the curve. And they each have their own equation, okay? So you just, when they ask you the question, you're gonna have to figure out where you are on the curve. And then from that information, you're gonna be able to figure it out, okay? Does anyone have any questions on this? All right.
Everybody's got it down.
Or extremely confused, which I hope.
I might be more with the latter.
Yeah. All right. So yeah, I should have said this in the beginning, guys and girls, but this, all the math associated with this and horizontal curves for that matter are, it's extremely simple math. We're just talking multiplication, division, addition, subtraction. It's just knowing when to do what. And if you really want to learn it, you need to know why. You know what I mean? Just getting that idea in your head of why you're doing this, that's 80% of your hurdle. After that, it's just high school math, okay? Just try to keep that in mind to stop yourself from being overwhelmed or not confident, because it is very simple stuff if you just understand a few good concepts. And that's how I tried to break this down. You know, given these 4 components to you, you know, this is the backbone of vertical curves. This is the whole concept right here. The other part of it is knowing the parts, that's just identifying stuff, and then really getting down in your mind that we're only talking about change in X value, not slope or curve distances. Okay. Just think of that alignment on that flat piece of paper. Okay. You would never know that there's a vertical curve or a valley or a crest on that road because the X values don't change. Your alignment values don't change, okay? And all right, the characteristics of a curve, I've already gone over it, but the idea of that vertical curve and that chord and your horizontal distance, all of those being split in two by a vertical line going from your PVI straight down. Keep this diagram in mind. If you draw a line from your PVI perfectly vertical down, you're going to cut everything in half. Everything's going to be, I don't want to say mirror image because it's not. That it is a mirror image with horizontal curves, but not vertical curves. But the distance values of everything is cut in half along that line, okay? And this is indicative of a symmetrical vertical curve. This does not happen if it's asymmetrical. That's why none of those formulas are going to work, and they're not going to ask you questions about that on the test, okay? All right. And oh, I like this idea too, the highest and lowest points on a curve. So if I have a crest and the highest point on this crest, well, that's dumb because that is the highest point. Okay, here's a crest, G1, G2. The highest point on this crest curve is about right here, right? And that point is the highest point because if I draw a perfectly horizontal line and I slide it down until it just touches one point on this curve, it's going to be the highest point, okay? So if I draw this horizontal line and I just slide it down, I keep moving it down until it barely touches my crest curve, it's going to barely touch at one point, and that one point is going to be the highest point on this vertical curve. The same thing goes with the sag. G1 coming in, G2 coming out. If I draw a horizontal line and I slide it up to where it barely touches my vertical curve, my sag curve, it's going to touch at one point eventually, and that one point is going to be the lowest point on it, okay? So given that concept, there's a formula that you can use, an equation that you can use that will find either the highest or lowest point. It doesn't matter if it's a crest or a sag. L times the absolute value of G divided by the absolute value of G1 minus G2 is going to give you a value, a distance value, and that distance value will be used to determine how far you go from your PVC along the curve, the X, change in X, to a point. So this equation will give you the distance you travel along your curve to get to that lowest point. It will not give you the elevation, but it will tell you where it is on your curve. Does that make sense?
Dane,
All right.
will you slide your phone over just a little bit on that top?
Oh, sorry, man.
No, you're good. Yeah, you were just kind of
Yeah.
right on the edge of the paper, and I just want to make sure.
Okay, yeah.
You're good now.
Okay.
Cool. Perfect.
All right. We're done with this at 6:30, Trent?
We are done whenever you want to be done.
Okay.
It's on
no,
you.
no,
bud.
no,
It's on you.
No, yeah, I'll go through an example real quick. I think it'd be good, and then we
Yeah.
could be done, unless
Yeah.
people have questions.
No, that'd be perfect. Yeah, real
Okay.
world math problems is always better. So,
Yeah.
yeah, I love that. And
Okay.
then I did share the PowerPoint in the Dropbox already. because I had that from the conference, and then the FS handbook that you showed at the beginning is also in that Dropbox folder. So
Okay, great. Thank y'all very much.
Yep.
All right. Okay, so here's a vertical curve, and we are given everything in this diagram, but we want to know three things. I want to know the elevation of my PVI. I want to know the elevation of my PVT, and I want to know the elevation of my midpoint on my chord. Okay. So let's see what we got here. We got a vertical curve. We have an elevation of my PVC is 100 feet. We have a stationing at that PVC is 10 plus 50. And I know my grade coming into that is 2%, aka 0.02 decimal degree. Okay. Then I have my curve, and I come to my point of vertical tangency, and my stationing here is 16 plus 50, and my grade coming out is G2, which is negative 3%, aka 0.03, negative 0.03 decimal degree. And that's all I have. Okay. That's all I'm provided are elevation, station, and my grades, and my station, my PVT. All right. And we also know all that we discussed. A vertical line from here is going to cut everything in half. We're only worrying about horizontal distances. Okay. All right. So what is my L value? I can figure that out right now. What is the change in X from here to here? I don't care about elevation. I just care about a straight line, horizontal line from one to the other. That's just going to be my change in X value. And I know that right off the bat. 1650 minus 1050, 600 feet. I know my L value is 600 feet. Okay. I also know if L value is 600, here's my chord. I know this line's cutting everything in half. So I know this half is 300 feet long and this half is 300 feet long. Okay. And I got my grades. I could do some math and figure out that I have a negative A value. Negative A means my grade change of grade is going to be a crest, which is what we're showing here. And that would be negative 3 minus positive 2, which would be negative 5. So that my A value is negative, and it is 0.05 negative. Okay. Let me see. I could figure out. Let me think. Okay. All right. So we got it all laid out. The first thing I want to know is what is my elevation at this point right here? Okay. PVI. So I could figure that out two ways. This point is an elevation along my back tangent, but it's also an elevation along my forward tangent, right? It's where they meet. So I could use either one of those equations to figure that out. This one's simpler. So let's use this one. That was y of my PVC plus grade 1 times X value. Okay. So I know my elevation of my PVC is 100. I know my grade of 1 is 0.02. Now, what is my X value? Well, I know it's 300 because a vertical line is going to cut my chord in half. I know the whole thing is 600 feet. So now I know that this distance, I don't know what this one is, but I know what that is, and that's 300, and that's what I care about. So x equals 300. So this is just 0.02 times 300 plus 100. And that would be 300 times 0.02 equals that, plus 100, 106. That is the elevation of my PVI. I know this grade, I know this where I'm starting from, and I know how far I'm traveling. Given all that, I know that if I travel all the way up to my PVI, I'm going to gain 6 feet in elevation. The elevation of this guy right here is going to be 106 feet. So we figured that one out. Next thing I want to know is what's the elevation of this point, PVT. Now, to figure out elevation of PVT, this point, if you think about it, is on my tangent, my forward tangent. I could use that equation, but it's also a point on my curve. It's the last point on my curve, right? So I could use my curve equation, or I could use my forward tan equation. I'm going to use the curve equation. The curve equation is the elevation of my PVC plus my G1 times the distance I want to travel plus my parabolic constant times that same distance squared. All right. So let's start plugging in our values. Elevation of my PVC is 100. That was a given. Plus G1, which is my grade of the line coming in, which is 0.02. Do not put 2. Times X. What is X? I want to know the elevation along the curve when I travel the whole thing. It's at the very end. So my X is going to be the whole thing, which is 600. Plus my parabolic constant times 600 squared. Same distance squared. So I got the only thing I need to figure out is what is my parabolic constant. Parabolic constant was G2 minus G1 times 2L. Oh, I'm sorry, divided by 2L. Let me make sure I'm right. G2 minus G1 divided by 2L. Okay. Okay, so I got to figure this out, plug this value into here. I can tell you right now, this value is going to be extremely small. Okay. And it needs to be small. And you need all the numbers associated with it. So I highly recommend you use your store function on your calculators. All right. So let's plug the numbers in. G2 is negative 0.03 minus G1, which is 0.02. So 0.03 negative minus 0.02 equals negative 0.05 divided by 2L. 2L, L is 600, so it'd be 1200. So that divided by 1200 equals 0.0000416667. Negative. Okay. That's my A value. That's my parabolic constant. It's really small and it should be, and it always will be. Okay. So plug that into here. So we can do everything with that number. I'm going to do store 1 on that parabolic constant. All right. So it's 100 plus 0.02 times 600 equals that. Store 2, 600 squared times my parabolic constant equals 15 plus recall 1 equals, oh, I messed it up. Let me see. 100. This is 12. 600 squared. Oh, there it is. Times 0.1234441. Okay, this will be plus negative 15. There we go. So 100 plus 12 plus 15 negative equals 97. 97. So my elevation of my PVT is 97. Okay. So if I go from here 600 feet, I'm going to be going down. And if you look at my diagram, not the one I drew here, but on my PowerPoint, you'll see that it is a little bit lower. It should be 3 feet lower. Okay. So we use the elevation along the curve equation to solve that. I could have used the elevation along this forward tangent too, if I wanted.
I was just gonna say that's a good check, right? So 300
Yeah.
feet times 3% is 9, which 106 minus 97 is 9. So yeah.
Yep, there you go.
Yeah.
So either way. So in this scenario, they asked for the PVI and the PVT. Well, those are kind of tricks because I could have used this equation to solve it. I could have used this equation to solve it, which we did. And then they asked for that. I could have used 2 others. Okay. The last thing we got to do is figure out what the elevation along the midpoint of my chord is. Well, that's not the equation that I provided. But if you just think about it, if I'm going from 100 feet to 97 feet, and I want to go halfway between them, I would just take the average of the 2, right? 197 divided by 2 is 98.5. So that's my elevation of my midpoint of my chord. And that was just simple math without an equation. If I'm going from this point to that point, and I change in elevation 3 feet, well, if I only go half the distance, I'm only going to change 1.5 feet, right? So there we go. Yeah. So does anyone have any questions about this or anything else that we discussed?
I'm sure there'll be a few
Yeah.
after everybody watches it.
Yeah.
Which I can throw in the chat, and if anybody wants to shoot you an email or something like that, they can certainly do that too.
Okay.
I will do that as a follow-up, as part of the follow-up email. So, but
Okay.
anybody who's on right now, anybody have questions? Anything they want to add? I
see.
I was gonna say, is anybody still watching?
I see Nicholas Skoloser. Is that how you say your last name?
Oh, sorry. 1 second. It's Slosher. Sorry.
Okay.
You can call me Closer. That's fine. How you doing?
Okay. Yeah. Yeah. I need to get back with you on
Yeah.
Yep, I will. It's been a hectic day. But
Don't even worry.
I plan on getting back with you. You said your first few lessons would be just kind of getting a taste for who needs what and stuff. So once you find that information out, reach back out to me.
Yeah, so just because there's a lot of people on this chat, I'll kind of give like a run through of like what we've done so far and kind of like our plan of action and how we want to be like effective with this study group. So basically the first one, we kind of like pin down a good time. It kind of meets with everyone, or that works for everyone. And then the last time we basically, it was kind of like improv, but we went over like a legal description. And like the ins and outs of a legal description, and we talked about Brown's book. I forget which one, but we talked about that, and then I gave like a situation that applied with work that week. And
Yeah.
then, yeah, so then we all took the 2020 practice exam. And
Yeah.
then we're going to go over on Thursday how we did and the areas that we could work on. The reason why I brought up the whole legal description thing is because there was a question that basically, if you were in that study group on Thursday, we basically answered it. That's kind of what we're doing. But I think that using you would be for the math portion would definitely be super beneficial. I know that not all of us are super great at math. Some of us are, but you definitely break things down really well. And just reach back out to me on when you're available, and then we'll schedule around you.
Okay. Yeah, sounds good. Thank you for inviting me. And I'd love to do what I can. I do a same kind of thing with my group here at Colorado Department of Transportation, and we do it every Thursday from 2:30 to 4 Mountain Time. So I didn't know if I could maybe incorporate them in it or not. So I'll get with them.
Are you is it online or is it in person?
Yeah, I do a Zoom call with my whole group, and I do exactly what we did here. I share a screen, and then I have my phone to show the math part.
Okay.
So yeah.
What day was that again?
What's that?
What day was that again?
It's Thursdays, 2:30 to 4 Mountain Time.
So it'll be 3:30 right now for you, Nick.
Yeah. Okay.
You're on the East Coast?
No,
No. Yeah, he's the West Coast, right?
Yeah, he's in Arizona.
Yeah.
So it'll.
Yeah. Awesome. Okay, then we probably could just work around you. Like we'll just we'll when we meet on Thursday, we'll talk about kind of our weaknesses, and if we identify like certain math weaknesses, I'll reach back out to you, and then we'll join on with whatever you have going on.
Okay.
So yeah, I think that'll work. So you said 2:30 to 4 Thursdays. So yeah, I'll after I meet with them on Thursday, I'll coordinate with you and then get the rest of the group hooked up. So yeah, no, I appreciate it. You really you do a great job. So thank you.
All right. Yeah. No, thank you. Yeah, don't let me forget. Keep hounding me.
Dane's a busy boy.
Yes, thank you. This was great.
Okay. Good.
Good stuff, Dane. I love it as always. It's you make it sound a little easier when you the way you approach it. So I do appreciate it. I threw your email in the chat, and then I will when I do the follow-up email too, I'll throw it in there for everybody as well. So
okay. Thank you, Trent. And I do apologize to everyone for being late again. That was
fine. No worries.
Yeah. I just got back from walking in the rain with my son. So
that's funny. I love it.
Yeah. All right.
Enjoy. All right, everybody. Have a good night.
See ya.
Awesome. Have a good week. Bye.